So now we'll be talking about Kepler's third law. And as far as your tests and content and things are concerned, this is the most important law. First and second law, you won't be tested on much. You won't be tested on any calculations for first and second law, but multiple choice questions maybe and concepts. But the third law is the most important one. It's called the law of periods, and you will be tested on calculations on this. Very much so. So in words, it's quite a mouthful. It's the cube of the mean orbital radius of the planets, and the proportion and the square of the period of the orbit is proportional. Or if you like, you can reword it to say the cube of the mean orbital radius of the planet is proportional to the square of the period of the orbit. But really, don't worry about those words, right? It's just like Newton's second law. It's a mouthful in words, but really they're just saying r cubed over t squared is equal to k, where r is the radius of the orbit. So basically, how far away the planet is from the sun. And t is the period, which is basically how long it takes to go around the sun once. So once you get your head around that terminology, then really, you wouldn't really need to write this in words usually. You just need to understand that the law basically is r cubed over t squared equals the constant k. That was Kepler's original idea because Newton hadn't come along yet. And this k just is a constant. And he's basically saying, as long as you're orbiting the same thing, in this case, they talk about planets around the sun, then you take the r and you cube it, you divide it by t and you square it, and they're all constants. And you have to remember, he's doing this 500 years ago without computers, without any sort of major sort of computational help or any sort of all this by hand, and also with all these rough measurements. So there was a pretty major finding at that point in time. Now, we're not going to derive this. I'm going to basically just focus on this for now. Why this is useful though, is because if you're going around the same sort of objects like planets around the sun, then that means radius, the orbit of, let's say, Earth, or cubed over the period of Earth, for example, or squared, is equal to the constant around the sun. But that's also true for the radius for, let's say, Mars, or cubed over the period of Mars, or squared, equals the constant around the sun, because they're both going around the sun after all. And because they're both equal to the constant around the sun, then it's much easier and much more useful for us usually to basically go, well, let's not really worry about what that constant is. You can just get rid of this and let these two equal each other. And we don't really need to worry about this k. Not really. I mean, we could calculate it, but we don't really need it. So in other words, a more useful way to use Kepler's third law generally is assuming you have two objects orbiting in the same thing, so planets around the sun or satellites around Earth, then instead of thinking of it as r cubed over t squared equals k, which is true, it might be more useful to think of it as r cubed over t squared for one object is equal to r cubed over t squared of the second object. And that is a very useful form of Kepler's third law. And we use that a lot for our calculations. Now, some of you might have concerns about the radius of the orbit, considering we just talked about Kepler's first law, which says that there is no radius in the sense that it's an ellipse, so it gets longer and shorter. And that's why, more technically, you put in the mean radius, the average radius. And you don't really need to worry about the technicality. Your exams assume that your orbits are circular. And so if they give you a radius, it is the mean radius, and you're just finding the best possible circle that fits that ellipse, basically. So you don't need to worry about that technicality, but that's how we get around it. So keep in mind Kepler's third law. It's r cubed over t squared for any one equals r2 cubed over t2 squared. Now, if you're using this version, we'll call this version 1, if you like, and you can probably see that the version 2 is going to come up soon, then feel free to use any units for r and t, as long as you're consistent. So you are free to use any units for r and t, as long as you use the same for the left-hand side and the right-hand side. And what I mean by that is, for example, r is the radius. You can measure that in meters. You can do that in kilometers. You can do that in miles. You can do that in feet, or in sort of more realistic terms, in astronomical terms. You might do it in astronomical units, which is the distance between the Earth and the Sun. You might do it in parsecs. You might do it in light years. Whatever unit of distance you want to do, if you do it for the first one and the second one, there's no problem. T is measuring time, so you could do it in seconds, you could do it in months, you could do it in days, you could do it in hours, years, anything. As long as you do it for this both, then it's fine. And this then really means that it's very useful for us, because we know, if we know three things. So for example, let's say we know the radius of Earth's orbit, and we know how long it goes around the sun once. So this is 1 year. And this we could kind of look up, but it's about 150 million kilometers, I think. Then in that case, as long as we know the radius of one other planet, then we can work out how long it takes to go around. Or alternatively, if you know, forget the planet, let's say that you want to do some science experiment and you want a satellite to go around the sun, so a satellite to go around the sun, but you want this satellite to be at a particular distance, which is now, let's say, 200 million kilometers. And for whatever reason, you want to put a satellite at that distance away from the sun, then we could then use this to work out how long it takes for the satellite to go around once already. We could just simply go, okay, 150 million kilometers, or cubed. I'm using million of kilometer as a unit, all over 1 year, or squared, which is Earth, must be 200 million kilometers, or cubed, all over the time, or squared. And then very quickly, I can just work out that t squared equals 200 over 150, or cubed. And that gives me 2.37, and I square root that. And that tells me it's 1.54 years. Very quick and easy. So immediately we can see, okay, if you know three of these things, you can work out the fourth. And that's very frequently how you use Kepler's third law. And you don't need to pay too much attention to the units we're using this version, as long as you're consistent on the left-hand side and right-hand side. Now, there's a second version of Kepler's third law that you'll find on your reference sheets and so forth. And it's a sort of more modernized version. And it's r cubed over t squared equals gm over 4 pi squared. Now, I won't derive this now. If you're interested in that, you can basically look at what we've done elsewhere. But this r cubed over t squared is the same thing as before. It's still the radius of the orbit divided by the t all squared. And basically, we've now got an expression for our k. You can see this is a constant. You should recognize capital G is the universal gravitational constant, which is 6.67 times 10 to the negative 11. Anytime in this topic, when you see capital G, you should see it as the universal gravitational constant, which is that number. Now, 4 is a number, pi is a number. Pi is just the 3.14 number. So all of those are numbers. M is the mass of the sort of central mass, or the sun in Kepler's case, but the central mass being orbited. So in other words, we've now not only, so when Kepler did his laws, he just recognized it was a constant, but he didn't really know what it was. It's what's called an empirical law. He wasn't really able to explain it. He just noticed it was a constant k. But now we can get this constant k in terms of certain things, particularly depending on the mass of the thing being orbited. And to derive this, you have to rely on Newton, who came up with the universal law of gravitation, but he kind of came after Kepler. So Kepler didn't have the benefit of Newton's sort of laws to help him out. Now, the key thing I want to stress about this version, which we'll call version 2, is you need to pay attention to your units. Because of the fact that on the right-hand side, we now are specifically working out K, and we're using the gravitational constant as well as the mass in kilograms, you no longer have the liberty of picking whatever units you want on the left. If you want these to match up, then importantly, your R must be in meters, and your T must be in seconds. And these are, of course, your SI units. M, meters, is the unit for distance, which R is, and S is the SI unit for period, which, well, is for time, which period is, and that's basically the second version. So now we can now link Kepler's third law with the mass of the object being orbited. As long as you pay attention to units, this is a second way you could use that, and you would use these to apply them to questions. And you've got a lot of example questions to work on in the worksheet. And this is the most important law because you'll be tested on this all the time. But that's how you use it.